Okay, so let's start with the exercises. I'll try to do it all in one take, but that's a bit unlikely. Also, I hope the orientation has been fixed. All right. Yeah. Question one is not is set of what is it? Yeah, it's ended back, so it's probably yeah. I'll check, but I think All right. So even though it's a question and you should know it because it's a property, the way to remember it is that inverse functions send it backwards and they expand, so they're typically the bigger one, right? That's how you can remember it. All right. So how do we show something as a subset? We show if it's a member, then it's a member, right? So let A belongs to A naught, then that implies what? That implies, well, okay. So does this imply F of A belongs to F of A? So I believe this is a one-way implication, right? This is a one-way implication always holds because we have the there exists here. The there exists happens to be A, right? So F of A is equal to F of A, and there exists A belongs to A naught such that you get it. So that's why this implication is it's always true. So now that we've got this out of the way, hmm. Oh yeah, I did mention though that this is equivalent to F inverse what? So F inverse of hang on. Yes, it's equivalent to saying that A belongs to F inverse of this set, which happens to be F of A naught. Correct? I said they're equivalent because of the formula. So what does that imply? Well, we've done one implication, right? Now we have to show that the other implication holds when it's injected. But what is this supposed to mean? This means that if there is, let's say, B is equal to F of A, right, and is equal to F of A prime, right, and so there has to be some A prime, something that is in A naught, right? It just need not be equal, right? So this belongs to A naught by F of A being in F of A naught. So there has to be some A prime. But by injectivity, A is equal to A prime. So what does that mean? That means A also belongs to A naught. So this implication happens to be both ways with injectivity. So yeah, that's how you show question one. Let's go with question two now. Yeah, I realized I was speaking a bit too fast, but I think that'll come with time. Okay. F of F inverse of B naught is a subset of B naught. That's it, yeah. So this is a member, right? So that B belongs to this. All right. So that means that there exists hmm, there exists C belonging to F inverse of B naught such that F of C is equal to B. Correct? All right. Oh yeah, the backwards implication probably holds because of surjectivity. Because for all C, we have B such that, right? Anyways, we'll get there. So hmm, now what? So C is an F of B naught. So F of C belongs to B naught, right? This is equivalent. So what does that mean? That's equal to B. So B is in B naught. So one way implication is done. Now for the backwards one, so if B is in V naught, right? and f of c is in B naught, where f of c is equal to B. And why is that? Okay, the backwards implication here is holding because of, okay, so what is, hmm. Yeah, the implication holds one way here because f of c isn't defined without surjectivity, right? Yeah. So, but the backwards implication holds by surjectivity because there exists a C such that f of c is equal to B naught. So we just choose that C, right? So I'll just add surjective. Okay. And this implies, yeah, so there exists a C, right? So what does that mean? That means f of c is an f of, hmm. Oh yeah, this is equivalent to saying f of c is an f of c naught, f inverse of b naught, right? So it's equivalent to this by definition of f inverse. And c is an f of inverse that. So, and we have a one-way implication here that f of c is in, so this implication is one way, but we can use it here. F of c, which happens to be equal to b, given our initial choice, is in f of inverse of b naught. So I think the proof is longer and could be shortened, but ultimately this is correct. I have got to have more confidence in myself. Anyways, okay. Question two. So preserving inclusions. Is it, yeah, F inverse? Okay. So this is actually quite straightforward. Let's see. Let's write it down. So this is by definition. This is by subset, and this is by definition again. So quite straightforward. All right. Let's go to the next part. Union. Okay. So what is the thing? Ah, okay. The sets are equal, right? So to show two sets are equal, you either use the formula or you show implications. All right. Hmm. So let's just go 1 to 2 first. B belongs to F inverse B naught union B1, which is equivalent to saying F of B belongs to B naught union B1. So, all right. So you fix, okay. So it can't be neither, right? So it has to be one of them. So here we're fixing, or say without loss of generality, you can take cases. There are many ways of approaching it. So you either take the case that it's in B1 or in B0, or you assume that without loss of generality, it's in one of them because it has to be in one of them. Otherwise, you're getting a contradiction. So from this, I'm just going to assume f of b is in p naught, right? You just fix it. You just assume one of them because otherwise it's a contradiction. So I'm just going to write that in brackets. And this implies this is equivalent to saying b belongs to f inverse b naught. And this at least implies b belongs to f inverse b naught union any set. But in this particular case, we can go with B1, right? And for the backwards implication, we're almost done. We just need to have the fixing here. The same fixing argument has to be done in backwards, right? So here, something like that. I don't know which one we used it in. And here, yeah, in this one. And this one holds from So this one's also true. When is it true? Yeah, we're fixing it here, but in the backwards one, it holds in generality. So it's still equivalent, right? I'll just fill this up, fill this up. I don't know. That was an attempt to make a cut. I don't know how successful that was. Should I have cut this out? Probably not. The blooper makes it better, I think. Anyways, yeah, so we proved both implications, and I'll try to prove the intersection using the same argument. Let's see. So, all right. Okay. So, intersection. Yeah, that's too great. Okay. So, if B belongs to B intersection this, and so this holds. Now, instead of fixing, we'll be writing and f of B belongs to FB1, right? So both of these are indeed equivalent to saying this. And this is equivalent to saying this, right? By definition of yeah, see, it's the curved thing, but the logical operator works too. Yeah, so the intersection is the same argument. Okay, so complement, right? Oh, I should not have erased it. Yeah, I should not have erased anything. It was the exact same argument. Okay, so let's write it down. Okay, yeah, the argument doesn't change at all. So we're just separating the thing, literally. And this entire thing works in both directions because this implication is both ways. But we'll soon discover that it's not always the case. All right. Yeah, I'll just not erase in case we have to repeat arguments. Okay, inclusion. So yeah, the argument for inclusions hold in a similar way. I'll just check which way is it. Yeah, okay. Hang on, which way was it? Oh, it's okay. Yeah, I should have just directly solved that. All right. I'm going to regret this, aren't I? Whatever. Okay. A naught subset of A1 implies f of A naught subset of f of A1. I do hope you can hear me. That would be a. Yeah, I'm just going to check if you can hear me. Yeah, okay. So I eased my paranoia, but ended the meeting in the process. Let's just go get back. Okay. So that A belongs to f of A naught. Uh, then what? So which way is it implied? Yeah, so there exists B belongs to A naught such that f of B is equal to A, right? Now, this implies B belongs to A1. So there exists the B belongs to A1 such that f of B is equal to A. So that means A belongs to f of A1, right? So you can hear me, I think. Yeah, I have no way of knowing until I finish the recording, actually, unfortunately. So yeah. So the implications results. And yes, unions are equal. All right, not inverse. Okay. Yeah, so it's a similar argument. Like A belongs to F of A not union in one, which means there exists a B belongs to A not union A1 such that F of B is equal to A. Now that means without loss of generality, B belongs to A0 slash 1. I might start using this, I'm not sure. Which means A belongs to F of A naught or A1, right? Which means A belongs to F of. I'm not sure if I want to use this notation, but this does look quite cool. So it's it's the without loss of generality fixing thing. But yeah. Now for the backwards implication, this implies we have to fix something, which means we just fix that. This is the case because it's a union, so this is implied already, right? Yeah. Here we're using the fixing, here we're using the fixing, and yeah, this is equivalent. So yeah, it works out. All right, intersection. Which way do we have to imply? Yeah, I would just do it directly. I don't really know the property. Okay. Anyway, so we just change it with and, we change this with and, we change this with and B belongs to A1. So far it's equivalent. So we change this with and 2. Wait, it's equivalent. I'll let you know what the problem is. See. Hmm. Yeah, so I'll just see what's not an equivalent. Okay. Oh yeah, is this one way? Hmm. Yeah, this might be one way. Not sure. Okay, so if A is in this, then this is true, fine. Is it equivalent? Yeah, it's equivalent. Okay. So B must belong to A naught and A1. It must belong to the intersection. I did write it down somewhere. Let's see. So it's when's the equality holding? It's when it's injective. Yeah. So the f of A's might be equal, but the B's may be from different sources. Okay. So there's no problem with this implication. Let's go backwards, I guess. Okay, A belongs to both of them. Fine, fine. So yeah, they're looking too similar that yeah, you might as well just treat them similarly. I hope you can get it from context. Okay. Ah, okay, okay. Yes, yes. Okay. So this is fine. This is indeed not true. This requires injectivity. Why? I'll show you. So A naught, A1, we have a B here and we have a B prime here, and let these two be the B that we have such that A belongs to A of F of A naught and F of A1. But since A is equal to A, f of B is equal to f of B prime, correct? But yeah, so the only way this B and B prime will lie in both of them is when they're both equal, which requires injectivity. So what does that mean? Yeah, so this B, they're not the same variable actually. They don't have to be the same variable. That's what I wrote down. So yeah, now complements. Also requiring injectivity, let's find out. So nothing so far. We'll have to change this up a bit. We'll have to change this up a bit. Right. Okay, so if B is an A naught minus A1, so B belongs to A naught. B does not belongs to A1, right? Okay, I'll try starting to write this instead. All right. So if B is an A naught and not in this, so what does that mean? Okay, from this we can definitely conclude that A is an F of A naught, right? Now, why should A not be an F of A1? So this is true for all B. So like what I just did is just negate the sentence, right? But this is it contradicting this? No, it shouldn't, right? Yeah. Oh yeah, but we have that f of b is equal to a, right? So yeah, we do have a contradiction here. To what? Okay, I should edit this out, but I just think of it. Yeah, never mind. Yeah, it was trivial. So this is equal to f of b, and I'm simply using the contrapositive, right? So given this, wait, which way is true? Yeah, this way is true. Hang on. Yeah, this is true. Hmm. Okay. Okay, this is hopefully my last attempt trying. So I'll just try to prove it by contradiction. So let's say f belongs to f of a1, which implies there exists a b belongs to a1 such that f of b is equal to f of a is equal to a, right? Is it the opposite inequality by chance? Oh, yeah, okay. Yeah, this is why I was stuck. Okay. Yep. Okay. Okay. Uh, I'm not sure if I want to cut it out anymore. This is pretty hilarious now that you see it. Okay, I'm just doing it all over again once again. Okay. This is why you always see the question, or at least, yeah, this is what happens when you try to prove something that's false. You get stuck. It's nice. Pretty cool. Also, it wasn't intersection, it was complement. Wow. Yeah, I should start clearing boards maybe. Okay. So A belongs to f of A naught. A does not belongs to f of A1. So there exists B belongs to A naught such that f of B equal to A for all B belongs to A1. F of B is not equal to A. So that includes the B that's lying in the intersection, right? Yeah. What does that mean? That means this B, can this B lie in the intersection, right? Can it be lie in A1 at all? It, okay. So can we get a B that's in A naught and not in A1? Okay, this B simply cannot be in A1, otherwise we will get a contradiction that f of B is not equal to itself. And therefore, so I'm just going to call it B prime, implies, so because of the contradiction, we can conclude that B belongs to A naught minus A, and f of B is equal to A, right? And given this, we can safely say that A is in f of A naught minus A1. Whew. Yeah, sorry about the mistake. Yeah. Now about the backwards implication, why do we need injectivity for it? Yes. So B is in here, equivalent to saying B is in A naught and B is not in A1, right? So B is not in A1 and f of B is. Okay, how do you show that it's not an f of A1? For all B in A1, should I try another approach here? I'm not sure. I'll start over for the backwards. So, okay, now we have to show that. Hmm. Okay, so let A belongs to f of A not A1, right? This means I'll just write a prime here. Ah, there you go. That's a contradiction. This is by injectivity. And what does that mean? That means B is not in A1, but B prime is in A1. And that's a clear contradiction. So because of that, A does not belong in F of A1. All right, that was a huge trial and error, and I hope to never do that ever again in my life. But it's going to happen again. So yeah, we show the other implication this way. All right, next question. I have absolutely no idea how much I'm going to include of that something. Composition. Let's go. No, not that. Not yet. All right. Question three. Okay, I'm going to do them orally. Let's see. So B part. Let's see. So I'll just write them once down. Yeah. So if B is an element here, that means what? That means uh, B f of B belongs to one of them, right? Some B, some fixed Bi, let's say, right? Now, because of that, B belongs to F inverse of Bi, and because of this, it belongs to the union, and it holds both ways. With C part, it's the same thing, but instead of one Bi, we'll say for all B, for all I, and for all I, and that means it's going to lie in the intersection. So nothing too different here. In F and G, the union, let's see, recording, right? Yeah. Okay. For F and G, F union A naught, whatever. Yeah. So A is in one. That means there exists B in union A such that F of B is equal to A. Now this B must lie in one of them. Otherwise, what's the point? Otherwise, it's not in none of them and it's not in the union. That's a contradiction. Therefore, it's in one of them. So you just fix that. Therefore, A is going to end up lying in F of AI for some of them, for one of them. So there, yeah. And this holds both ways because we're choosing them. We're changing the fixing argument. Okay. Intersections. Let's see. So it's in all of them now. A is in one, B is in all of them, B is in all of them. So you can split it up. Yeah. Okay. And it doesn't hold backwards because we're going to have some yeah, same thing. The primes need to be equal. So they're going to be BIs, right? All the BIs need to be equal for this to work for the backwards one. So yeah, it's just the generalization of the argument. And yeah, I'll just write it properly so that you don't get confused. This is what I'm ultimately solving. And you just use the definition in question 6 of the previous exercise to understand the solution better. But yeah, it's not too hard, given that we solved a certain specific case. Okay, yeah, that's pretty easy. Okay, so GOF inverse C naught is equal to G inverse F inverse C naught, right? Okay, yeah. So let C belongs to this. What does that mean? That means GOF of C belongs to C naught, correct? That's an if and only if by definition of inverse images. And what does that mean? That means f of C belongs to G inverse of, cool, okay. G inverse of C naught. That's also an if and only if by definition. And this is also an if and only if C belongs to F inverse of G inverse. So straightforward. All right. If F and G are injective, show that GOF is injective. All right. Pretty straightforward. Let's see. So yeah. Is it if and only if? Yeah, not yet. Fine. So GOF of A is equal to GOF of A prime. By injectivity of G, F of A is equal to F of A prime. And by injectivity of F, A is equal to A prime. And so we're done. Now, if this whole thing is true, right, what can we say? C part. Yeah, so I took way too much of a break. Uh, Also, I was stupid, so I'll just write down the entire argument. Right. And we're given, right. So let G not be injective, right? What does that mean? That means the only way that's possible is if there exists A and A prime such that there must exist a pair A comma A prime for this to be the case, right? I'm changing the quantifiers. There's an implicit for all here, so I'm changing that there exists, right? Now this directly actually implies that A prime is not equal to A. Why? Because take the contrapositive. Yeah, A prime is equal to A implies F of A prime is equal to F of A. This is true because of rule of assignment. So the contrapositive is true because it's logically equivalent, and this is a direct contradiction. So G must be injective, right? And a similar argument holds for F. I'll just check. Yeah, a direct argument also holds for F. Let's see why. So uh, F of, so what does that mean? F of A prime. Yeah, if that's the case, then yeah, F of A is equal to F of A prime. And this implies A is not equal to A prime, right? There exists A comma A prime. Well, we simply take G of both of these, and we've gotten a pair that's equal, right? Because by rule of assignment, and this implies, so it directly contradicts the injectivity of GOF. So both F and G must be injective. That's what we can prove. All right, surjectivity. So GOF, so for all C belongs to C, there exists A belongs to A such that GOF of A is equal to C, right? Okay. So, so why must okay. So first of all, we'll prove that G must be, wait. Oh, we have to show that, right? Yeah. To show that given G and F are injective, surjective, right? So, so for all C and C, we have B and G, B such that G of B is equal to C by surjectivity of G. And there exists A belongs to A such that F of A is equal to B by surjectivity of F. And therefore, there exists a B belongs to B such that f of A is equal to B and G of B is equal to C, which means A comma C belongs to is satisfying the rule of assignment, and therefore, for all C in C, since C was arbitrary, there is an A in A such that G of F of A is in C. So this is where the rule of assignment is used. So yeah. Now let's try proving that G or F. G is surjective given that this is surjective, G O F. F need not be surjective, and I'll show a counterexample. I'll like to call it the wormhole. Not the wormhole discussed in that one. Leave that one. Okay. Yeah. So so it's given to us that for all C and C, there exists in A such that G O F A is equal to C. So what does this mean? This means there exists B belongs to B such that G of B is equal to C and F of B is equal to A is equal to B, right? But this is precisely what it means for G to be surjective. So we're done. And as for why F need not be surjective, I'm just drawing figures, but it should illustrate the point. You can make any concrete example you want. So this is an identity map between F to something, and G is any larger set that doesn't, you know, F need not be surjective. G is surjective because it's covering the entirety of it, and GOF is surjective because it's a sort of identity map. You can make whatever map you want. You can even make shift it and get it here, right? Any example works out, and it need not cover the whole space, right? Also, how am I running out of ink already? Okay. So yeah, to summarize, if GOF is injective, then G and F are both injective and G is surjective. And if G and F are bijective, then GOF is bijective. That's pretty much it. Yeah. And and it's probably not if and only if, yeah, both G and F need to be surjective for GOF to be surjective. So yeah, that's how it's summarized. All right. I really wish I could just put it here, but it's done. Okay. Yeah. So first problem seems easy enough. So GOF is equal to identity A, right? Or is it the other way around? Yeah. Yeah. And FOH is equal to identity B, right? So I didn't observe that the identity function is a bijective function, right? It's a bijective function and it sends everything to itself. I am not proving why it's bijective. You can do that on your own. And yeah, so because it's bijective, G and F are both injective by the previous theorem, and G is surjective by the previous theorem. So what does that mean? Well, F is injective, so we're done, right? We're done with that. And F is surjective because G is surjective. So this function is the the outside function is the one that's surjective. So F is surjective. So what does that mean? Yep, that proves A part, right? Yes, give a function of a example of a function that has a left inverse and no right inverse. So in order for it to have no right inverse, it must not be surjective, right? Because if it is surjective and has no right inverse, then that contradicts the proof of the theorem we just did. So we just need a 1, 1 function that has a left inverse that is not surjective, right? So I'm just going to draw a map because they're examples and you can attach whatever numbers you want, whatever letters you want. Ultimately, it doesn't matter. Yeah. So not surjective, you just send it to anywhere, right? And the inverse function is going to be the left inverse is, yeah, that needs to be surjective. So if you want, so the inverse function is defined backwards in these points, and if you want here, right? So what do we get? This is insurjective, this is surjective, this is injective too. No, this is not injective now, right? And it doesn't have a right inverse because of that. Okay. Yeah, also the compositions are the identity function, so you'll have to check that. So, basically this part is never reached, so it comes back to itself. All right. Give a function that has a right inverse and not a left. Yeah. So I'm going to do that drawing again, but this time it has to be surjective, right? And not injective. So let's make one. So this these points are just anything you want, right? Hmm, something like that. Yeah. Now, okay. So the function, yeah. So if we take the function h, which is defined here to here, right? So it goes here. This is the function h. It will have a left inverse, which would be f, right? Because it's defined here. But yeah. So h and this is f. FOH is equal to identity, but of this set, right? And yeah, the same thing applies here. Can we have more than one left inverse or more than one right inverse? I think we can only have one of what. Okay. So yeah, we can have more than one right inverse because H could have been, yeah, H could have been any three of these, basically. There's no difference. So we have more than one right inverse. For the left inverse, what about the left inverse? Let's see. I think we only have one. Let's just take this and yeah, I think we can have more than one left inverse too. Just, these points can go wherever they want, right? And they're never accessed, essentially. So yeah, both are possible. I hope I'm right here. I'm not checking. Hmm. Yeah. So if F has an left inverse and a right inverse, then F is surjective because it's surjective and injective and therefore bijective. And because it's bijective, F inverse is bijective. Why is F inverse bijective? Because yeah, the proof is direct. I think the book does cover it, but yeah, the proof written in English is the proof. Uh, yeah, I don't know what to do. So F inverse is bijective and G is bijective because composition of two. So what? So GOF is the left inverse, right? Yeah. So because the identity map is bijective and F is bijective, uh, G will be forced to be bijective. You can surjectivity and injectivity actually directly follow. So G is bijective directly. For FOH, it's a little trickier. So it's injective by the theorem. It's surjective because F is surjective. So you'll have to work a proof, and I am not doing that. So H and G are both bijective. F inverse is bijective. We just have to show that they're equal, right? Yeah. So to show that for all A, G of A is equal to H of A equal to F inverse of A. That should do it, right? So let's just let A be arbitrary, right? And okay. So it's clear that F inverse and OF is indeed identity, right? So they match up. Okay, yeah. So all I'll take is G. OF is equal to F inverse OF is equal to identity, right? Okay. Can I just treat them like groups? I'm not sure. I mean, okay. So we do know that these two are equal, right? Oh, no, they're not equal. Hmm. Okay, so this is equal to identity of, okay, I'm just going to write this down. F is a function from A to B and A to B, B to A, right? So identity of A, correct? Yeah. And F inverse is equal to identity of B. Okay. So identity of A, all right? So what's identity of A composition of F inverse, right? F inverse is going to be a function from B to A, essentially. So it's going to be a function. So that's equal to F inverse. That we can use. F inverse is going to be a bijective function from B to A, right? Okay. And so F inverse is equal to GOF inverse is equal to F inverse OF inverse, right? And G is a function from, they both a function from A to B to A, right? So yeah, I think this might directly prove it. Hmm. Let's see. This is equal to what? This is equal to identity of B composition G. And is that equal to G and F? So G is a function from B to that. So yeah, essentially nothing's changed, right? That's equal to G and that's equal to F inverse. And yeah, by a similar proof, I think we can prove that H is equal to H inverse, that F inverse. Now, what am I using here? How can I just do it? So we're taking the rule of assignment and yeah, so we're taking the rule of assignments at identity function, which are trivially true by the definition, and that's what's allowing us to use them well enough. Basically, these two, and these two are yeah, they're taken to be trivial. Essentially, the proofs are in the book, the extra details. But yeah, I think this is a good enough proof. Okay, what's left now? Question 6, right? Okay, I'm not too interested in this question, but all right, this is high school math. Yeah, so the graph is something like this, I believe. Correct me if I'm wrong, I don't know. It's 0 at 1, 0 at 1, so yeah. And it's what at 0? It's also 0 at 0. Wait, what? 0 at 1, 0 at 0. Oh, and not at -1 and at -1. Okay, that's a bit sad. So the graph is wrong. So that probably means it's going to be something like this. Yeah, that should do it. Okay, when it's at, yeah, it's 0 at, the derivative is 0 at 2 points. So yeah, it's going to be 1 by root 3 or something. All right, that's it. Thank God. So what does that mean? That means, yep, there are a bunch of options. So you can take this part, right? You can take this part, I believe. So the thing is, you can take any part you want. You can even take any part in the middle. and you can make an inverse function at any point if you want. So yeah, but you'll essentially be restricting the domain, which is exactly what the question is asking you to do, and the range would doesn't quite matter, does it? Or no, we do have to restrict the range too to make it surjective. But yeah, the idea is this, and to compute it is too well computed. I am not doing that. So yeah, that finishes the exercises.